So, gentlemen, we have a fundamental law in physics called the conservation of energy, which states energy cannot be created or destroyed. Instead, it's transformed from one type or one form to another. Okay? And we looked at this when we looked at work. If you do 500 joules of work, you lose that 500 joules, it goes into some other object. It could go into the kinetic energy of an object, or it could go into heat. Generally, it's a combination of the both. We can restate this, gentlemen, that the total energy on a system is always a constant value. We can also restate it by saying this, that the sum of all energies initial prior to some interaction is going to equal the sum of all energies final. Okay? And we're going to look at a couple of different models where energy is in different forms and we're converting between the two. In this next box, gentlemen, we are going to say that our total energy is the sum of all forms. That is EP plus EK plus, we're going to use E lowercase f for friction to represent heat. Okay? Please stop talking and get this written down. Now, mechanical energy, could you just write underneath, is easy to be transformed. We can lump potential and kinetic into mechanical energy. Mechanical energy is the sum of potential and kinetic. Okay? The example of why it's easy to be transformed is because I could stand here with a ball. I could throw the ball up into the air. And in doing so, we are converting it from kinetic to potential. That's easy. If I give the ball 10 joules of kinetic energy, as it rises up, it's doing a lot of things. It's slowing down, so it's losing its kinetic. And that's because it's gaining height, it's gaining potential. So it's transferring it from movement energy to stored gravitational potential energy. And if we ignore air resistance, if we ignore friction and sound, I could say all of it's converted. Okay? All 10 joules of kinetic has been converted to 10 joules of potential, and it gets to its highest peak, and then it falls back down, converting it back to kinetic. Bless you. However, all right, that's enough. However, once it smacks the ground, it then produces heat. Okay, the contact patch, it makes a bit of sound, bang, bit of internal friction, the object is going to heat up slightly, the surface is going to heat up slightly. What we call that is heat, which is a low-grade energy. Because it's difficult, not impossible, but difficult to convert back. Okay, so here's my wonderful example. Well, I'm not going to throw that. Here's a wonderful example. Here's my tennis ball. I throw the tennis ball up in the air, potential to kinetic, bang, 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 gone. It did a couple of bounces. It hit first and then it still had it. It went up a little bit of potential, a little bit of kinetic, bang, bang, now it's stationary. All of that energy is gone. Okay? It's gone into random chaotic motion of particles on the surface of the carpet, surface of the glue stick, and even in the air as well. When we heard that, when it hit the ground, that's energy traveling out in a sound wave. Right? And that sound wave carries that energy away. It hits the wall, it hits the carpet. It might make the surfaces of this room slightly warmer. That the molecules in the carpet, when the sound hits them, they might start jiggling just a tiny bit more. Not enough for us to go, whew, it's sweating in here. The curtains are not going to raise their temperature by 40 degrees. Okay? In fact, they won't even raise enough for us to measure it, but that's where the energy's going. Now this model couldn't be formed until you had the atomic model. or the kinetic theory that all things are made of little things that jiggle, and they're in constant motion, and the temperature is a measure of how fast the particles are jiggling. Once that model in chemistry was made and developed, then they could go, well, that's where the energy's going. Okay? It hasn't disappeared. The caloric hasn't sort of flown out of the object. It's just gone from. And one other way to think of mechanical energy is, and I think I explained this to you the other day, it's kinetic energy in harmony. So if I throw an object this way, with a mass and a speed, it's got all of its particles are moving in that direction. They're all working together. If I added up all of the molecules, they have mass and they have a net movement that way. That's their sum of their kinetic energies. However, the glue stick is at room temperature. It's at 25 degrees, which is a measure of the mean translational velocities of all the particles in that glue stick. It has internal energy. It has heat. Okay, so all of the molecules are also jiggling backwards and forwards in random directions with random speeds. Okay, but that's energy in chaos. Okay, it's a measure of entropy. It's a measure of disorder in the system. So it has heat energy, and in this classroom, gentlemen, I could not get the energy out of this glue stick. I could not say, glue stick, I want you to drop by 20 degrees Celsius and convert it to potential energy, and all of a sudden, like a snake charmer, and it's getting colder and colder and colder. Can't do that. Okay? However, it's not impossible. I could take this glue stick to a region where the environment is a lot colder. I could take this glue stick to Antarctica, where 20 degrees Celsius in a minus 80 degree environment, this would be like a hot water bottle, and I could get the energy out. Okay? I maybe would be able to convert that heat energy into mechanical energy. So the steam engine is a good example. A petrol engine is a good example. You're making a whole lot of heat. You're exploding a gas. Well, let's go with petrol energy. You're taking a gas, you're turning it into a vapor, you're mixing in oxygen, a little bit of a spark, bang! It makes a whole lot of heat. That expansion pushes a piston outwards. That's work. That's a force acting over a distance. So we would say that the gas does work, and that work turns the pistons, turns the engine, makes your car go. But it's incredibly inefficient. Okay? Only about 20% of all the chemical energy actually goes into making your car go. The other 80% makes your car really, really hot. Okay? So your engine will get up to hundreds and hundreds of degrees Celsius. And if you don't have a method of removing that excess heat, then it's going to make your engine break and warp and crack. Okay? So that's enough about mechanical and heat energy. Let me know if you have had enough of the air conditioning, and we'll turn it off. Let's consider this. We looked at this example in our previous worksheet, but let's just go our 10 kilogram. Obviously, we've got weight and normal force, which would be 98 down, 98 up, but we're not displacing it in that direction. What we are displacing is 100 newtons this way, and I'll just go 30 newtons backwards, okay? Because our displacement is 5 meters that way, okay? So really, it's only the force in the direction of the displacement that's doing any work, okay? The normal force or the weight force is not doing any transfer of energy here, okay? So the work done on the crate, that's going to be the sum of all forces. So I would say that the sum of all forces here is plus 100 plus minus 30, possibly because I assigned my conventions that to the right is positive. So again, the crate doesn't realize that there's two warring forces. It doesn't know that there's a 100 Newton war that way and a 30 Newton tug of war that way. It just goes, I'm a box, I'm feeling 70 Newtons that way. And that's the energy that it gets. Okay, so it says, I'm feeling 70 Newtons. So we would say the work done on the crate is the unbalanced force on the crate. So it gets 350 joules. Okay. The work done to friction, well, that's the force of friction that acts over a distance, and that was 30 newtons times 5, which is 150. And as I said last week, you would have noticed that when we looked at the concept of work, where is the energy going? It's coming from a person, it's going somewhere else. That's the applied force. So the person is applying a 100 Newton force over 5 meters, 500 joules. Okay? And then you should notice that the sum of your energies equals the total. Okay. Now we could look at the total energy of the system. The system could be the entire diagram. We would say that the total energy is the sum of all forms. And in this case, we're not worrying about its potential energy. We'll just assume that it's staying at the same height, h equals 0, so there's no potential energy. Then we can check that 500 does in fact equal 350 plus 150. But again, you could almost slice that off and say that has been removed from the object. Okay, it does not go to the objects. So the object cannot play. Again, that's the smear of heat left behind. The friction has caused the surfaces of both the crate and the floor to heat up. The surface of the crate might be a few degrees higher than the rest of the crate, but again, it's random chaotic motion of molecules. We cannot take that energy like the snake charmer. What do you call it? Snake charmer? Like the snake charmer, and go and make the crate go any faster. Okay? So, after the 5 meters, we have an equation that relates kinetic energy with speed of an object. We could then rearrange V equals the square root of 2E over M. I'm skipping a few steps there, but we wrote these down last week in the previous booklet. We would multiply both sides by 2, we would divide both sides by M, and then we would take the square root. So we could figure out the speed. Well, that's going to be 2 lots of 350 divided by 10, square root of 70, 8.36. 36? 37. 8 point what? We need an arbiter. Go, Mahoney. It's too difficult, I'll do it.
8.366.
8.37. Oh. All right. Now, because you are all very, very smart young gentlemen, let's consider this person has applied this. They've pushed the cart with their head. There's 2 ways to look at this. I'll give Jabon just a moment to compose himself. Did you just bra me? Bra. There's 2 ways to look at this. Before we looked at the concept of work and energy, you could have done Newton's second law. You could have said, oh, I know the unbalanced force is 70. I know its mass. I know its acceleration is going to be F over M. I know that its acceleration is going to be 7 meters per second squared that way. I also know S. I can figure out V. I could figure out V squared equals U squared plus 2AS. So I could use my SUVAT, and we could have gotten exactly the same answer using acceleration. But this is a different way to look at it. You could look at how much energy. So instead of force over time or force, well, this is still force over distance. You could look at how its energy is increasing over distance and figure out its speed that way. And sometimes in year 11 and year 12 tests and exams, it will say, determine the speed using concepts of work and energy. In which case, you cannot go down the Newton's second law path. You cannot use SUVAT. You have to use these equations. Now, let's suppose that once we get to here, the person obviously lets go, maybe because it's going too fast. Now, all of a sudden, there's only one backwards force, that being 30 newtons. So we just figured out that it's traveling that way, it's going to start to slow down. Okay? So we've put it in the acceleration period where it's gaining energy. It gains 350 joules. Now, every meter it slides, it's going to lose 30 joules. 30, 60, 90, blah, 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 blah. You get the idea. We can figure out how far it travels. Every meter it travels, it loses 30 joules. So let's go down to, suppose he let go after 5 meters. Let's just redraw the diagram down here. I realise I should have redrawn it down here. Please don't. No, you're not. Now, we could say that the work is the change in energy, which equals energy final minus energy initial, which we can equate to F times S. Now, we know it's change in energy. It started with 350, it ended up with 0. So it's lost 350. But we could say S equals you would get 0, subtract 350 over 30, and it'll tell us how many meters, 11.7 meters. I hope to 3 sig fig. I'm pretty sure we've got all of our 3 sig fig here. 11.7 meters. Of course, we're making the assumption that V equals 0, therefore E final equals 0. Once it slides along, comes to rest, it's got no more energy, the force of friction has been deducting every meter, a negative 30 joule transaction. Okay? Alrighty. Let us consider a skater in a half pipe. But oh, what's this? A skater on a half pipe. Now, I've paused it for now. Grid lines, measuring tape out. We don't need the measuring tape. Put them over there. Potential energy reference. Pie chart. Everyone likes pie charts. But what I also like is bar graphs. They excite me. All right. I'm going to place him just here. Okay. Uh-oh. What have I done? Turns out it won't let me do that. Okay. Now, on Earth, let's press play or where's the play button? There we go. Here we go. Wow. Lag. I blame the NBN. Gentlemen, this should really be happening in real time. Could we just close our mouths, open our minds? This is happening, it's struggling, okay? It's screen capturing and, you know, it's tens and tens of megabytes of RAM are needed for this. Okay, we are ignoring friction for now. This is an unrealistic scenario whereby there is no friction and there is no air resistance, okay? So we are not making any heat. The mechanical energy in this system is remaining constant. The mechanical energy is potential plus kinetic. All right. So what you might notice, and we can analyze this person's energy at any position we want, but obviously there's some maximum and minima. If I paused it right at the top, close enough, you will see that all of his energy, total energy, is in the potential column. He's not moving at that point. On that half pipe, he would be stationary, and then he'll start to accelerate back down. If we know his mass, and if we know the height that he is at, which at this moment is just over 6, and his mass is 75 kilos, and he's in a gravitational field of 9.8, then we can say we know his energy. And if he's stationary at that point, we know his total, because we can say that EK equals 0, the total equals potential. Boom, I know the total energy of the system. Okay? Then, let's analyze it at the bottom. Have a look at what's happening to the bars. They are swapping.
Is it just me, or does it, when you get to the bottom, the rate in which they change gets higher?
Yes, because he's travelling faster.
Okay.
Yes, absolutely. Now, At the bottom, we make the assumption that the height he is at is 0, therefore he has no potential, and the total is now equal to his kinetic. Now again, if we know his kinetic energy, one more chirp out of you, Joseph, I'll be asking you to leave. One more bit of talking from you, I'll be asking you to leave. I don't want you talking while I'm talking. Thank you. We make the assumption that he's at the ground. He's got no potential. Therefore, his kinetic is known. His mass is known. We can figure out the speed that he has at that point. But it gets even better. I could stop it at any point. There. I just paused it at random. If I know the height that he's at, I know his potential. If I know the total and his potential, then I can figure out his kinetic. And then if I know his kinetic at that point and his mass, then we can figure out his speed at any point along the half-pipe. Okay? But again, we've got to use the tricks. The trick is that at the top, he's got maximum potential, 0 kinetic. So, and we'll look at thermal, we'll come back and have a look at thermal in just a moment. Let's go back to this skater on the half-pipe. We're going to analyse his position here, here, and here, just as I said, at two extremes. At this point, gentlemen, could you please say EK equals 0, EP equals E total?
So ignoring friction.
Ignoring friction. At the bottom, we're going to say that EP equals 0 and that EK equals E total. And then at part 3, well, we'd need to know, I will have to print you off one. Sorry, just pay attention. I might have only printed 21 copies. That's terrible of me. Sorry, Tristan. Gentlemen, at the top, let's figure out what the total energy is. So we're going to say that your total energy is EP plus EK plus EF. We're going to cancel out, and I'll say at 1, we can say at the start his total energy is in the form of mgh, 50 by 9.8 by 4. He's got 1,960 joules of potential to do work. Okay? Because it's stored energy. Now for now, we're going to say that that is locked. Remember the conservation law says that the total energy in a system is constant. Okay? I did have this drawn here, 4 meters up. Doesn't really matter. Okay? So, assume that this gentleman then drops into the half pipe. Get the wheels. How does he look? Pretty good. Okay. Now, there, gentlemen, one way to think about this is that there was a downwards force, and that downwards force is weight, and it was allowed to act over a downwards distance of 4 meters. So if you said that his weight force, which was 490 newtons, was allowed to act over 4 meters, then the work done by gravity is weight times h, mgh. And that just, again, 490 times 4, we said it comes out to 1960. So, the work done by gravity on him is 1960. He gains a positive W value now. He gains that energy. He now has it in the form of kinetic energy. Okay? So let's have a look at point 2. I'll just color code, you'll probably be annoyed, I'm just going to color code this blue. Okay. We make our same statement, ET equals EP plus EK plus EF. Again, we're assuming EP equals 0, EF equals 0. we can then say EK equals 1960, or equals ET. Square root of 2 lots of his energy divided by his mass, and that will give him a speed. If he's 50 kilos and if he's got a kinetic energy of 1960, then he has to be travelling 8.85 meters per second. Okay? Now, at point 3, let's now suddenly turn friction on. Okay? So, I know this is unrealistic, but now we're going to say friction acts. From this point forward. Maybe it's a weird half pipe where the first half of the half pipe is perfectly smooth and no friction, and then all of a sudden it's made of grass or turf or carpet or something. Just imagine. We're just going to turn on. Now, obviously, if there was no friction, then all of his kinetic would go all the way back to potential. It would be a perfect transaction, and he would get back to the same height. And that would be the applet just playing forever. We could go back and look at it, and he would just be still going backwards and forwards every time, getting up to exactly the same height, never losing any mechanical energy. Now he is going to lose mechanical energy. Let's now say that he is observed to travel to a height of 2.4. H final 2.4 meters. Okay? So let's now make our statements. Our total energy if that's his maximum height, we're going to set that V equals 0. Can I control V? Where did he go? No, have I? No, I might just have to copy him again. Okay. All right, we're going to say V equals 0. And from that statement, we can say that he's got no kinetic energy at that point. Now, since we know his height, we know his potential. Since we know his total, we can figure out the energy that he's lost. So basically, you say he started with 1190, or whatever it was, 1960. He's now got something. The difference is how much he has lost. But again, you can't just do it in your head. You can't just write the answer down. You've got to show your working. So we're going to say E final equals the total energy, subtract what it's not. That's 1960 minus mgh. Yes. That gives us 784 joules removed. Okay? And if we know the length of the ramp, we could say the average frictional force would be that divided by S. We could use our work equals F times S. So that was the work done to heat or friction. And if it acted over, F times S equals that number. But again, as Mahoney observed, your friction is directly proportional to V. So the faster you're going, your frictional force will be greater at this point and less at that point. What we could attempt to find is the average frictional force, but understanding that it does vary with speed. Okay? If we go back to this horribly slow applet, if we were to track friction, so there's a little slide bar here. If we were to track friction, let's just do it now. Okay, what you'll notice is here comes the thermal bar, and it's growing at the greatest rate is when he's traveling faster. So yes, majority of the energy is taken out at the bottom. And now you'll notice, well, pausing is not working. Now you will notice that the green and the blue are playing with between each other. The total mechanical energy is transferring, but you can't get any back from friction. So what you'll notice, if the green and blue are continually getting smaller and smaller, our two observations are he's not getting as high up the ramp and he's not travelling as fast when he's at the bottom. Okay? Oh, okay. How did I? Well, I didn't mean to. Let's go back to this. This is a terrible simulation. Did you just say that to get a laugh out of Gage?
His skateboard is too wide for the bottom of that half pipe.
I know. It's a terrible simulation.
His wheels are also in the ground.
We'll be here. We'll be here a while. No. We'll be here a while. All right. Let's go to another fun video. Yes. I'm risking it for the biscuit, Tristan. This guy is... My statement also applies to you three. Shush. Watch this guy for a bit. Let's hope that it streams. And he's very gifted at drawing curves and circles very well.
Now I want to return to the conservation of mechanical energy. I have here a pendulum. I have an object that weighs 15 kilograms and I can lift it up 1 meter, which I have done now. That means I've done work. MGH is the work I have done. I've increased the potential energy of this object. 15 times 10 is about 150 joules.
147.
If I let it fall, then that will be converted to kinetic energy. If I would let it swing from 1 meter height, then you would be there and it would hit you, you'd be dead. 150 joules is enough to kill you. They use these devices, called a wrecker ball, they use them to demolish buildings. You lift up a very heavy object, even heavier than this, and then you let it go, you swing it, thereby converting gravitational potential energy into kinetic energy, and that way you can demolish a building. You just let it hit, and it breaks a building. And that's the whole idea of wrecking. So you're using then the conversion of gravitational potential energy to kinetic energy. Now, I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that ball from a certain height, then that ball can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here.
If you gave it an initial speed, then the total energy is then EP plus the EK that he gave it. And that would be a force acting over a distance. He would be doing work on the system, and then when it came back, it'll have EP, but it would still have that residual EK. So he's got to be very careful that he releases it without giving it any motion. Okay?
I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then This will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep on mine. 3, 2, 1, 0.
This is not a
Physics works, and I'm still alive. See you Wednesday.
Now, last year, I was looking for a very similar video, and I came across. In fact, I was watching Neil deGrasse Tyson redid Carl Sagan's Cosmos. Carl Sagan was an educator back in the 80s and 90s, and he came back and redid it last year. And calm down. Now, where he actually is I imagine it's a very famous lecture theatre in a British university. At the Royal Institution. It could have been Oxford, Cambridge. He might have followed where Isaac Newton once would have taught. But he basically stood there, he's talking about the laws of science that were discovered, and he took the pendulum and he spoke about potential kinetic conservation of energy. He released the ball and it came back and just booped him on the snoot. And I'd seen this video, and I remembered the TV show, I remembered the episode that it was from. So I Google searched Neil deGrasse Tyson, conservation of energy, and I'm showing this to my class in YouTube. Ready? Okay, so one more time. Okay, so someone had obviously photoshopped that. That never actually happened because the laws of science differ fundamentally. Bang! Right in the. All right. I'm just going to add the word assume here, just to make that correct. How much longer do we have?
About 7 minutes.
I need to check your homework. So let's shush. I know you're getting excited. Let's just do this last question, and then, gentlemen. No. Oh, no, I've got them thinking about homework, getting them all excited. Let's do this first. Okay. Let's consider this object finishes here, v equals 0, at a certain height. It had an initial height of 1.5. When you throw an object, it leaves your hand. It's not leaving it from h equals 0. It's actually a certain height. It's got potential already. Then we give it kinetic. So what we're going to do here, we're going to determine at the start, we can say that the total energy is EP plus EK plus EF. Again, assuming no energy losses, we can simply go MGH. Now, I gave this to a Year 11 class. I didn't give them the mass, and they got all upset because they couldn't quantify how much energy does it have. We could go MGH plus a half MU squared. That's M by 9.8 by 1.5 plus a half M 15 squared. We can leave our expression in terms of M. It's got 127.2 M joules. Not to be confused with millijoules. Whatever M is, here's an expression for the total energy in terms of mass. So if it was a 1 kilogram object, boom, it's got 127 joules. If it was a 0.1 kilogram object, it would have 12.7 joules. If it was an M kilogram, then it's got 127 M.
So could we just say, okay, let's say
You could, and a lot of students do this. Let's just say, let M equal 1. And then it becomes a nice number, and then they transport that number over to the finish. But what you will see is that the mass does not factor in. Let's go to the finish now. we would say that the total energy is EP plus EK plus EF. Since V equals 0, we can cancel out the kinetic energy. We get that the total energy, all 127 M joules, is now in the form of potential energy. It's at its highest point, it's got its maximum potential, it's stationary, it's got no kinetic. We can say that 127.2 M equals mgh. What do you notice about solving for this question? The m's cancel. So we could therefore say, or H final equals 127.2 divided by 9.8 gives a height of 13.0 meters. So interesting enough, the mass is not a factor. Sure, the energy is proportional, but I could have done the same thing with a 100-gram mass, left at 1.5 height, 15 meters initial, it will get to 13 meters. I could take a 2-kilogram mass, sure, I would have to do more work, but if I could get the 2-kilogram mass to leave my hand at 1.5 at that speed, both 2 kilograms and what they will both ascend to the same height. They're both transferring the same rate, different amounts, but mass is not a factor. Okay. Now we've got 3 minutes left. Is that correct?
Yeah.
All right. I would like to check your homework.